So we have the this nice assembly of our mouse, and we have all the parts inside. Okay, and I will focus first on this component here. Okay, this component is the wheel support. This component helps us to do the center click, okay, and to move up and down when we have in a Word document or in a web page. One curiosity or one requirement for this component is that the wheel will be supported in these 2 points. Let me isolate this component. It will be supported in these 2 points, okay, and the force that the user will do when he performs the center click will be applied in these 2 points. So for the designer, this is a critical region in the structural requirements. So we should be careful about the defects and the quality of the part in everywhere, but in particular in this region here. So let's start the design. I will do some mistakes, okay, on purpose, just in order you can see how to predict defects or how to analyze a defect. Okay, so let's start. As I said, the first thing we should do is to define the part we want to produce. We are going to define the material. We have a database, extended database of material and a group organized by groups, and then every group contains different type of materials. As Ken and James mentioned, we have signed an agreement recently with Embase, and we will have access to an extended material database in the near future. So once we define the material, we will define the melting temperature, let's say 260 degrees, and I will start defining my process. So the first thing I should do is to define the gate location. So I will place a gate just here. The gate size will be 0.8 millimeters of diameter. I can change the shape of the gate, the location, the radius. So as I say, we are using geometry to define the problem. So at any time, I can modify not only my gate or runner or mold, but also my part. And this is very convenient for a designer. I will explain why later on. So once we have defined the gate, I will go quickly to the process definition. I will define the filling time, let's say 1.2 seconds. I will tell, don't stop the process if I am exceeding any machine parameter. I don't want to set up anything about packing or cooling right now, and I will hit the run button really quick, and the simulation will start. Okay, so just to sum up what I have done during the setup, I select the part I want to produce. I place a gate, and I defined some very few process conditions like the filling time, gate location, and I just launch the simulation, defining only that I will use the fast mode of the simulation. So as far as the simulation starts, and I have 10% or 20% of the simulation, I can call my results, and I can start analyzing the results. So as you can see, the simulation in the fast mode is extremely fast, okay? And we can have a result in very few seconds. So I'm computing this solution, this simulation live in front of your eyes. And as you can see, the solution is taking less than 20 seconds, okay? Of course, the part is small, it's simple, but just you can get an idea of the calculations time we are managing in our fast solver. So we can see a green flag here. It means the simulation has finished. So I will reload my results, and I will play to check the evolution of the temperature. For example, I can check filling time through all the part. I can check the pressure to produce this part. I can check the temperature at the core, temperature at the shear heating layer. I can check velocities, air traps, and in particular, I'm interested in weld lines. So as you can see, Inspire Mold is showing me where the weld lines will be located. As you know, weld lines is generated by material that is arriving from different fronts to different regions of the part, to the same region of the part, generating a kind of weld material, okay? As I told you at the beginning, this is a extremely complex region because we have the mold wheels being supported here, and it's in the structural behavior of the part, it's very important to keep this region safe. Not, of course, all the regions should be safe, but this is in particular important. So as you can see, we have a weld line that is contacting this point very close to the critical region, so this is not convenient. So what to do in this case? And it can be extended to any part that we are designing. So basically we can go back to the runner system design. I can remove this gate. I can place a new gate in other location with the same size. I can hit the run button and perform a new iteration. So what the software is doing is taking into account the previous configuration with the new gate. He's launching a new analysis to compute a new simulation of this particular part with the new gate location. Okay. So it will take, again, another 20 seconds, 30 seconds to run the full analysis, and we will be able to see the results. I have the results ready here, so we don't need to wait even 20 seconds. So let's see how the filling is going on right now. So now you can see filling first this region. Of course, the gate is located here, and we can see how the material evolves inside the cavity. Let's check filling time. Now you can see the filling time is more homogeneous through all the part. And let's go to check what we are interested in weld lines. So now we was able to remove weld lines from this particular location. Now weld lines are located here, here, and here. And we have the ability to add gates in other locations, multiple gates, trying to move these weld lines away if we consider this is decreasing the structural behavior of the part. But this is the real advantage. We can perform multiple iterations in a very, very, very few amount of time. And not only that, once we have optimized the position of the gate, we can go back to our running system design and we can say, okay, now I want to produce a mold with multiple cavities. So I want to create a 4-cavity mold. Okay, so I will place my gate, and Inspire mold automatically will come out with a full design of my runner, distribution, and the 4 cavities located using the best practices of the mold industry. So these diameters are computed based on the thickness of the part, on the size of the part, and on the filling time we are defining. We can change this. This is parametric setup, so we can say, no, I want to have increase the distance between my parts. So I will hit create here, say I will remove the current. Yes, of course. I select again my surface, and now I have increased the distance between my parts in the mold. And of course, we can basically define the process. As you can see, the filling time now increase. We can change it, and we can perform the analysis for the multi-cavity mold, considering the sprue, runners, and gates, and my complete system. So this calculation may take around 2 or 3 minutes. So I have also this calculation already performed. And again, we can understand the evolution of the material, how the material is getting warm during the filling, evolution of pressures during filling. I can measure, or I can plot the pressure at the injection BC to see how the pressure evolves during the filling process. I can check the evolution of temperature, weld lines, air traps, and so on and so forth. So this is a way to use Inspire mold right from the initial design stage. But also we would like to know more advanced data from my process. I want to know what will be the deformation of the part after the molding. I want to know what will be the packing time, if I will have sink marks and these kind of things that are included on a detailed analysis. So what I will show you now, let's go back to the original geometry, and I will select a different geometry, a different part of the mouse to do this particular analysis. So I will go now for this cover, the internal cover, okay, that is this component here. I will set up again the material. I will set up gate. In this case, I will use 2 gates. 1 gate in this location, 1 millimeter, and 1 gate in this location, again 1 millimeter. I will set up a mold, so I will create the mold. I will place a cooling line. I may require a cooling line here, so I will use cooling line creator. As you can see, by doing a couple of clicks, I can define the path for the cooling line, and the cooling line will automatically be created. I can change the diameter. Let's say I want to have 4 millimeters diameter, and I will move the cooling line closer to the part in order I can extract heat with better performance. I could create inserts, vents, and multiple components. So next, I will define the process. First, I will run the fast analysis again to check the front flow, and then once I have a great idea of the gate location, I will perform the detailed analysis. So I can set up again my filling process. Once I'm done, I can perform the fast analysis. I only need to select fast and the average thickness of my part. That will be enough to set up the fast problem. By hitting the run button, the simulation will start, and I will show you what will be the result, okay, of the filling of this part by using these 2 gates, for example. So I have 2 gates, so of course we'll have some weld lines on the center that may not be convenient. I can check the temperature during the filling, so temperature distribution looks quite nice, not too cold the material. But if we see again weld lines or end traps, that could be a problem to have a weld line right in the center of this rib that is supporting the force that the user is applying on top of the mouse. So that is not convenient. So what we can do again, we can change the gate location, and we can see again the front flow evolution. If I place a gate at the side of the part, we can go back again, change the gate location, and put a gate at this location here. So now we can see how the material flows by using this gate position. So as you can see, to create different possibilities or different iterations is extremely easy. So what about the advanced features, about the detail features? Okay, so basically the only thing we need to do, the setup to have a detail analysis is exactly the same. We should set up, of course, the packing stage, what will be the packing time, packing pressure, and cooling time, so ejection temperature and end time for the calculation. Okay, and we can the only extra thing we need to do is to define this as a detail run, and I can perform packing, cooling, and work page analysis. And even if my material is already set up to use fiber reinforcement, I can also add fibers during the filling to predict the material properties at the end. So basically, I will hit the run button. Of course, the calculation time will increase. This is not our fast solution, this is our detailed solution, but the accuracy will increase, and the solution I will have will provide much more information than using the fast solver. Okay. One very important thing is that the mesh is automatically generated, so we don't need to define any kind of layers or any kind of assigned element size on any particular geometry. Everything will be automatically defined. And as you will see, the mesh is created considering multiple layers through the thickness. So we are ensuring 5 layers on the thickness. We are ensuring concentric boundary layers on the runners, gate, and sprue. So the quality of the mesh is extremely good, and everything is automatically done in background. So what can we see here? Again, we can visualize. I will turn off the mesh. I will add a cut section here and the X plane. So what we can do here is we can visualize again the evolution of the front flow, considering the runner, sprue, gates, and how the material is filling the part. We can see the pressure, we can see the temperature. As we are using multiple layers, you will see that how the shear heating is affecting the temperature in the part. So we are considering the shear heating effect during the filling. You can see evolution of velocities, pressures, filling time, well lines, etc. But this is very similar to what we can provide with the fast solver. But what is the difference? That we can now check, for example, the packing stage. And in the packing stage, we will be able to predict the pressures during the packing, okay, how the pressure is changing during the packing when we have the gate solidified, so we cannot pack more material. We can predict sink marks that will be generated during the packing. So you can see how the ribs in the background are creating some sink marks on the skin of the part, and you can detect really deep sink marks or critical sink marks, and these sink marks are because of probably the highest thickness that we have in this particular region. As I said, as a designer, I can always go back to my preprocessor and I can modify or edit the geometry, trying to eliminate or mitigate this kind of defects. In this case, this part is hidden behind the cover of the mouse, but just imagine we have sink marks in a part that is the user can see, so this should be avoided. So by editing the geometry, the original geometry or designed geometry, we can avoid critical defects. So let's go back to the results, and I want to show you a couple of very interesting things in the detailed analysis. So as I say, we can evaluate the filling, we can evaluate the packing, we can evaluate the cooling process. Okay, so how the part is cooling down after the filling. So as you saw, I have added cooling lines to my mold. So as you can see, we will be able to evaluate and to optimize the effect of the cooling lines inside my mold. So as you see, I have added a couple of cooling lines on the top side of the mold, and we can see the effect that is creating this cooling line. So the top part of the mold is cooled, and the bottom part of the mold is hotter than the top part. I do this on purpose just to show you the difference between or what we can achieve by adding cooling lines. And the advantage is, again, that we can, at any time, we can go back to the preprocessor, we can select the cooling lines, and we can edit or modify the location or the shape or create new cooling lines in my model. So let's go back to the final stage, that is the packing process. Okay, the work page. So in work page, we as designers, is extremely interesting for a designer that will show us, because packing will show us the variation on the geometry that the part will suffer after the production, after we remove the part from the mold. So the idea is to show how much deformation we have, or how the part is being deformed after we remove the part from the mold. This is, of course, I'm increasing the deformation in order we can see. So it's multiplied by, I think, by my factor is, I'm using 50 as a factor of to multiply the deformation. But this will allow us to see the tendency, and also to measure the deformation that the part is showing after the molding. So I can go here, I can select my tool, measuring tool. I can click this location here. I can select this location here, and I can see how this is changing during the cooling stage and after removing the part from the mold. So as you can see, we have the original size, or the original dimension, the design dimension, and after the cooling, we have a different dimension. So this is extremely useful for the designers to compensate the deformation of the parts after the molding.